Assalamualaikum warahmatullahi wabarakatuh. So today we are going to continue with our physics topics, nuclear physics and nuclear radiation. So we are going to learn about the constituents and structure of nuclei, radioactivity and the decay processes, half-life and radioactive dating, nuclear binding energy, nuclear fission, nuclear fusion, practical applications of nuclear physics. These are the learning outcomes. You may refer these learning outcomes from your lecture notes. Okay, the first topic, the constituents and structure of nuclei. The properties of nuclei is given here. Okay, I think you already know all of this because you have learned this in your school before. The atomic number Z is the number of protons in the nucleus. The neutron number N is the number of neutrons in the nucleus. The mass number A is the number of nucleons in the nucleus. Okay, so A plus Z plus N, where the mass number equals to the atomic number plus with the atomic number with the neutron number. Nucleon is a generic term used to refer to either proton or neutron. The mass number is not the same as the mass. Okay, this is the graphical representation for the nucleus. Okay, the symbol is X is the chemical symbol of the element, A is the mass number, Z is the atomic number. Okay, example for aluminium 2713. Okay, the mass number of aluminium is 27, the atomic number is 13. Okay, and then the atomic number also represent the number of proton inside the element. Okay, if the atomic number is 13, so the proton also 13. Okay, and then the balance 27 minus 13 equals to 14. 14 is the neutrons inside the nucleus. Okay, the charge, the proton has a single positive charge, E, positive E. The electron has a single negative charge, negative E. The amount of charge is E equals to 1.60217733 times 10 to the power of negative 19 coulomb. The neutron has no charge, hence make it difficult to detect. Okay, and then one more thing is the isotope. The nuclei of all atoms of a particular element must contain the same number of protons. They may contain a varying number of neutrons. Isotopes of an element have the same Z, okay, but different N and A value. Okay, for example, the isotopes of carbon 12, carbon. Okay, for carbon they have the same proton number, but different number of neutron. Okay. This is the carbon 12, this is carbon 13, this is carbon 14. Okay, the amount of proton in our isotope are the same, which is 6, but the amount of neutron will be different. Okay, the mass, it is convenient to use unified mass unit U to express masses. Okay, so 1 unified mass unit equals to 1.660559 times 10 to the power of negative 27 kilogram. So it is convenient to use unified mass for the nucleus. Okay, for example, if we want to measure our weight, we are more convenient to use kilogram. If we are to measure the weight of a lorry, we usually use ton. Okay, right. Okay, and then mass can also be expressed in a mega electron volt per c square. Okay, so it is from the Einstein's equation, E equals to mc square. And then one unified mass unit also can be represented by this value 931.4 0.94 mega electron volt per c square. This is the mass of a unit. This is the unit of a mass, okay, not a unit of an energy. Electron volt, yes, is the unit for energy, but electron volt per c square is the unit of a mass. Okay, this table shows the masses of the proton, neutron, and electron in various units, in the kg unit, unified mass unit, and mega electron volt per c square unit. All of these units are the unit for mass. Okay. For nuclear stability, there are very large repulsive electrostatic force between protons. The nuclei are stable because of the presence of another short-range force called the nuclear force. Okay. For example, inside the nucleus there are lots of protons. Okay, so you have learned before that if two particles have the same charge, then they will repel each other. Okay, similar to the nucleus. Okay, the proton inside the nucleus will repel each other, but why they are very stable? Because of the short-range force called the nuclear force. Nuclear force will bind them together. Okay, like nuclei are most stable if n equals to z. Okay, and then heavy nuclei are most stable when n is greater than z. As the number of protons increases, the Coulomb force increases, and so more nucleons are needed to keep the nucleus stable. Okay, no nuclei are stable when z equals to or greater than 83. Okay, okay, you may refer to this diagram, the graph of neutron number n versus proton number z. Okay, we proceed to the topic of radioactivity and the decay processes, and half-life and radioactive dating. Okay, radioactivity is the spontaneous emission of radiation. Experiments suggested that radioactivity was the result of the decay, disintegration of unstable nuclei. Okay, there are three types of radiation can be emitted. The first one is alpha particle. Alpha barely penetrated a piece of paper. If you can see here, this is the alpha particle. It is barely penetrate a piece of paper. The particle are the helium nuclei. Okay, actually alpha particle is a helium nuclei. Okay, consists of 2 neutron and 2 proton. Okay, the second one is beta particle. Beta can penetrate a few millimeters of aluminium. Okay, so this is beta. It can penetrate a few millimeters of aluminium. The particles are either electrons or positron. Okay, a positron is actually a positive electron. It is not a proton. It is a positive electron. Okay, electron is negative, but positron is a positive electron. Okay, again, not a proton. Okay, a positron is the antiparticle of the electron. It is similar to the electron except its charge is positive. Okay, the last one is gamma rays. Gamma is not a particle, it is a ray. Okay, this is a ray. Okay, it can penetrate several centimeters of lead. Okay, the rays are high energy photons. Okay, it is a photon, it is a ray, it is not a particle. Okay, so the other important thing is the decay constant. The number of particles that decay in a given time is proportional to the total number of particles in a radioactive sample. Okay, delta n equals to delta lambda n delta t. Okay, where lambda is called the decay constant and determines the rate at which the material will decay. Please do not confuse with the wavelength. Okay, lambda is a Greek letter. It can be symbolized as anything. Okay, so for this case, it represents the decay constant, not the wavelength. Okay, so this lambda is decay constant. Okay, the decay rate or activity R. Okay, R is the symbol for decay rate or the activity in this case of a sample is defined as the number of decays per second. So the activity equals to delta n over delta t equals to lambda n. Okay, the unit of activity R is curie. Okay, symbolized by Ci. Okay, 1 curie equals to 3.7 times 10 to the power of 10 decays per second. The SI unit of activity is the becquerel. BQ, 1 becquerel equals to 1 decay per second. Therefore, 1 curie equals to 3.7 times 10 to the power of 10 becquerel. Okay, half-life. The decay curve follows the equation. Okay, n equals to n naught exponential negative lambda t. Again, lambda is the decay constant. The half-life is defined as the time it takes for half of any given number of radioactive nuclei to decay. So this is half-life represented by t half equals to ln 2 divided by the decay constant equals to 0.693 over the decay constant. This is the graph of the number of radioactive nuclei versus the time. Okay, this is the half-life. Okay, this is the second half-life. Okay, we proceed to the next one. Decay processes. The first one is alpha decay. When a nucleus emits an alpha particle, it loses 2 protons and 2 neutrons. Okay, n decreases by 2, z decreases by 2, a decreases by 4, because alpha particle is a helium. So it has 4a and it has 2z. Okay, so the first element that we call it a paranucleus. Okay, paranucleus will produce the daughter nucleus after the decay. Okay, the paranucleus will emit the helium and it will produce a daughter nucleus with less 2z and less 4a. Okay, for example, the decay of radon. Okay, radon 226. Okay, radon 226 with 226a and 88z. Okay, before the decay, but after the decay it has 222a and only 86z because it released the 4,2 helium. Okay, this is the equation. Radon 226 88. Okay, radium it has produced the radon actually. Okay, 222 86 radon plus with 1 helium. Okay, this is the decay processes for beta decay. During beta decay, the daughter nucleus has the same number of nucleons as the parent, but the atomic number is changed by 1. Okay, symbolically, this is the paranucleus, this is the daughter nucleus with less 1z but the same a plus the electron, okay, plus antineutrino. Okay, or it if the decay release the positron, then it must be together with neutrino. Okay, the symbol is the symbol for the neutrino. V is the symbol for the neutrino. V bar is the symbol for the antineutrino. Okay. To summarize, in beta decay, the following pairs of particles are emitted: an electron and an antineutrino for this one. the first equation, the electron must be emitted together with the antineutrino, and then the positron must be emitted together with the neutrino. Okay, the emission of the electron is from the nucleus. The nucleus contains protons and neutrons. The process occurs when a neutron is transformed into a proton and an electron. Energy must be conserved. The properties of the neutrino: zero electric charge, mass much smaller than the electron. Recent experiments indicate definitely some mass. It has spin of half, very weak interaction with matter. Okay, this is the decay processes for gamma decay. Okay, gamma rays are given off when an excited nucleus falls to a lower energy state. Okay, similar to the process of electron jumps to lower energy states and giving off protons. The protons are called gamma rays, very high energy relative to light. The excited nuclear states result from jumps made by a proton or neutron. The excited nuclear states may be the result of violent collision, or more likely of an alpha or beta emission. So this is the example of a decay sequence. The first decay is a beta emission. Okay, the second decay is gamma emission. Okay, this is the beta emission. The C asterisk indicates the carbon nucleus that is in excited state. So during the beta emission, it produces the excited carbon nucleus, and then this excited carbon nucleus must be stabilized. And then how to stabilize the excited carbon nucleus? We need to emit the gamma ray, okay, during the second decay. Okay, the decays will continue until the stable nucleus is reached. Okay, this is the diagram of the series of alpha and beta decay in the decay chain. Okay, you may refer to this diagram in your lecture notes. Okay, this represents the alpha decay, this represents the beta decay. Okay, in beta decay, the mass number will not be changed, only Z number will be changed. Okay, nuclear binding energy. Okay, the total mass of a nucleus is always less than the sum of the masses of its nucleons. The total energy of the bound system, the nucleus, is less than the combined energy of the separated nucleons. This difference in energy is called the binding energy of the nucleus. It can be thought of as the amount of energy you need to add to the nucleus to break it apart into separated protons and neutrons. Okay, for example, this is the binding energy of tritium. Okay, tritium is actually hydrogen 3 1. Okay, so before it has a mass of 3.01604 unified mass, but after it has the energy of 3.025155 unified mass. Okay, so there is a change of mass, and before and after the process, the decay process, and then the difference in energy is called the binding energy of the nucleus. So there is a change of mass here. We insert this mass into the Einstein's equation, equals to mc squared, and then we can get the energy released during the process. Okay. Actually, this is the amount of energy that we need to break the protons and neutrons apart. Okay, this is the binding energy per nucleon. Okay, as you can see here, the binding energy per nucleon mega electron volt versus the mass number A. The most difficult element to be broken apart is this one, nickel. It has the highest binding energy, followed by the germanium and the ferrum. Okay. Process of nuclear energy. There are two processes of nuclear energy. The first one is nuclear fission. A nucleus of large mass number splits into two smaller nuclei, and then the other one is nuclear fusion. Two light nuclei fuse to form a heavier nucleus. Large amount of energy are released in either case. So this is nuclear fission. A heavy nucleus splits into two smaller nuclei. The total mass of the products is less than the original mass of the heavy nucleus. The sequence of events in nuclear fission. You can see here the uranium-235 before the fission. Okay, the neutron is absorbed by the 235 uranium nucleus, changing it to 236 uranium, which is a 236 uranium nucleus in an excited state. Okay, and then the nucleus deforms and oscillates like a liquid drop. After the event, there are two lighter nuclei and several neutrons. Okay, so fission of uranium-235 by a slow or low energy neutron is given by this equation. Neutron, okay, hit the uranium-235 and it will produce the uranium in the excited state, and then the fragment of fission will be produced with the element S and element Y plus neutrons. Okay, the chain reaction. Neutrons are emitted when the uranium-235 undergoes fission. Okay, one incoming neutron causes a fission event in uranium-235 nucleus. This is uranium-235 nucleus, and then these neutrons are then available to trigger fission in other nuclei. Several neutrons from the initial fission event cause fission in additional uranium-235 nuclei, and then the number of neutrons and the number of fission events grow rapidly. This is the chain reaction. Okay, the principle behind the nuclear bomb, where 1 kilogram of uranium-235 can release energy equal to 2,000 tons of TNT, the material to make a bomb. Okay, so this is the last one, the nuclear fusion. Okay, nuclear fusion occurs when two light nuclei combine to form a heavy nucleus. So for fission, we split the nucleus, but for fusion, we combine the nucleus. The mass of the final nucleus is less than the masses of the original nuclei. This loss of mass is accompanied by a release of energy. All stars generate energy through fusion. Okay, all stars including the sun. The sun, along with about 90% of other stars, fuses hydrogen. Okay, so the advantage of using fusion reactor is inexpensive and safe fuel source. Water is the ultimate fuel source. If we are going to use nuclear fusion for our power generating system, then water will be the ultimate fuel source, because in water is H2O, right? So H represents the hydrogen. This hydrogen can be combined using nuclear fusion, and then a great amount of energy will be produced. Okay, this is the energy produced from fusing the hydrogen nucleus. Okay, it has happened in the sun. Okay, the nuclear fusion process in the sun begins with two protons fusing to form deuterium, and then fusing with the third proton to form helium-3. Okay, this is the equation. Okay, helium plus with the helium. Okay, will produce the deuterium. Okay, and then after that a helium-4 nucleus is formed in one of the following two ways. Okay, and then considerable energy is emitted in this interaction. Okay, but still the fusion technology is not still not a reality, so we are still in the research stage to make fusion a reality and materialize in the future. Okay, last topic, topic 337, the practical applications of nuclear physics. We can find the application of nuclear physics in several medical applications and also in the military. Okay, in the magnetic resonance imaging, medical radioisotope for imaging and therapy, identification of materials, dating of materials, power generation, and the weapon of mass destruction. Okay, that's all from me. Thank you for watching.